In this lecture, we'll continue our discussion of electrochemistry. You'll want to have on hand the chem activity from Thursday, chem activity 46 on redox reactions, the chem activity 48 on the electrochemical cell, as well as a pen and pencil, calculator, perhaps some scratch paper. So let's first do a mini redox review. So this is a redox from our last class session. We want to remember what an oxidation reduction, what's abbreviated to a redox reaction, does. Atoms that lose electrons are being oxidized. You want to remember that if their oxidation number has increased, it's become more positive, which means that they've lost electrons. Atoms that gain those electrons have been reduced because their oxidation number goes down, becomes less positive because they've gobbled up those electrons. Here's a real-life redox reaction of our old friend table salt. You've got two atoms of sodium in its solid form reacting with diatomic chlorine gas to form this ionic solid, sodium chloride. This is a redox reaction because, as we notice, we've got both of our atoms in the first reaction in green in their elemental form. That means that they both have oxidation numbers of 0. But if we look over to the right at the product, we see that sodium has lost an electron to become positive, while chlorine has gained an electron to become negative. Overall, for each one sodium atom, it gives up an electron because it's being oxidized, and for our diatomic chlorine, each one takes an electron to form 2 chlorine ions, being reduced. If an atom is being oxidized, another atom, it better be being reduced. Oxidation and reduction go together like peanut butter and jelly. You've got to have one, you got to have the other. The atom that is being oxidized is the reducing agent. So you want to think about, if I say that I'm being oxidized, that's a noun. I'm the one being oxidized. However, I am reducing something else, so that's more of a verb. Same thing goes if an atom is being reduced, it must be oxidizing something else. Keep in mind that reducing agents and oxidizing agents are always reactants because they are acting on some other reactant to form a product. Now, we typically split these redox reactions like we did in the previous slide. We split them into 2 separate half reactions so that we can look at oxidation and reduction separately. Oxidation half reaction always has electrons as a product because the reactant is giving away electrons. On the other hand, reduction always has a half reaction that includes electrons as reactants because in reduction, the reactant is gaining electrons to form something else. Let's take a look at this example. We've got a nice reaction here, again involving chlorine in its diatomic form, also water and our iodine ion. We look at our oxidation states and we can start identifying what's being reduced and what's being oxidized. So we remember that diatomic chlorine is in its elemental form, so it's got an oxidation number of 0. I- tells you right there with that minus sign, it's a 1- charge. The other thing we want to remember is that all halogens form 1- ions. If we look at water, we want to remember that oxygen in most compounds, the ones you'll need to be worried about, are going to form a -2 ion. So we want it to be charge neutral because notice there's no charge listed in the upper right of water. That means that each hydrogen is a +1. If we go to the product side, we see we formed our chlorine ion in the -1. We take a look at the oxygen. You've got 3 of them. Each one of them is a -2. The overall compound carries a -6. Or sorry, the overall compound carries a -1, but the oxygens are actually in total a -6, which means that the iodine now is a +5. Whoa. If we look back at the left, iodine was a -1, and now in the products, it's a +5. That is a big loss of electrons. Then we look at our hydrogen ion, which hasn't changed from left to right. So what's being oxidized is that I- by a whole heck of a lot. It's losing 6 electrons to form that I5+. What's being reduced? Well, it's our old friend chlorine. Now remember, electronegativity-wise, this is going to make sense because chlorine is above iodine in that whole scheme of group of family, right? So the things that are in the upper right of the periodic table are the most electronegative. And in a fight between chlorine and iodine, it is not going to be I, it's going to be Cl. So Cl actually rips electrons off of I, as we see here. Now, how do we balance redox reactions? Well, that's another reason why we get the half reactions going. We first balance each half reaction for its atoms. Then we look at how the electrons are balanced, because remember, there are no extra or deficient electrons. We have to have the equal number for both half reactions, which means we might have to do a little bit of multiplication. First thing we want to do with our redox reactions is to assign oxidation states. First, we determine which element is oxidized, and there must be another element that's being reduced. We write our oxidation and reduction half reactions, and we always keep track of those electrons. Oxidation electrons are on the right because they're being produced via oxidation. Reduction, however, is consuming electrons, so they should appear on the left as a reactant. First, we balance our half reaction by mass. Going easiest, let's take a look at H and O. Then, if we need to, we can add some water, we can add some H+, and then if the reaction is done in base, we might need to worry about neutralizing. There's lots of examples of this in both the required reading and in the day's activities. Then you want to balance the half reactions by charge, and you do this by adjusting the electrons. You want to balance the electrons between the half reactions. You want to add the half reactions and check that those actually cancel. And what do I mean by cancel? Well, the electrons should cancel from left to right of the equation. And you can make sure that you've got the same number of atoms of a particular type on one side versus the other. Then you want to make sure that all your charges make sense. If you've done your half reaction work correctly, number 7 is a piece of cake. Now, your redox reactions involve the transfer of electrons from one substance to another. This is the definition of redox. Therefore, redox reactions have the potential to generate an electric current, because if you've got moving charges, like electrons would have to move from one thing to another, if those charges are moving, that means you've got a current. Now, we're going to want to use this current. Think about all the stuff that you're currently surrounded by that requires power. Your phone, maybe a computer, maybe you're sitting near a lamp. There's a lot of stuff. We're going to need to separate the place where the oxidation occurs from the place the reduction occurs, because we're going to want to actually capture the current somewhere in between. What's current? Current is the number of electrons that flow through a system per second. The unit that's officially used is an ampere. You might have just heard it shortened to amp. 1 amp, capital A, of current is equal to 1 coulomb of charge flowing each second. Now, that equates to a lot of electrons per second. Don't worry about memorizing this number. Constants are always provided to you. An electrode's surface area is going to dictate the number of electrons that can flow. Larger batteries produce larger currents. You know this. Small stuff takes small batteries, big stuff takes big batteries. And sometimes, if you're unlucky, have you ever bought something that takes like 19 AA batteries? It probably would have been better if they just required 2 or 4D batteries, right? And that's because, again, how much of the chemicals you have actually dictates how many electrons flow. And now, because you've gone through how redox reactions work, you know why. If we want a lot of electrodes, we're going to have a lot of reactants. And that just requires bigger battery, bigger electrode. Now, what's voltage? The difference in potential energy between the reactants and the products is the potential difference. Here we use the unit of volt. 1 volt is 1 joule of energy per coulomb of charge. It's the voltage needed to drive electrons through an external circuit. The amount of force pushing the electrons through a wire has a special name called EMF, or electromotive force. Electrochemistry specifically is the study of redox reactions that produce or require an electric current. The conversion between chemical energy and electrical energy is carried out in an electrochemical cell. That's a battery. Battery in your car, battery in your cell phone. Heck, defibrillators have batteries in them. Diabetes monitors for blood sugar have batteries. There's so many things with batteries, we kind of forget that they're around. But battery is actually a shorthand name for electrochemical cell. Now, if we want energy, we probably really want a spontaneous redox reaction, which is called a volcanic cell. These are also known as galvanic cells. These are the kind of things that actually occur in electricity out, and they do not require us to input electrical energy. Now, they're going to have a bunch of chemicals, and they're going to react and do redox, and we're going to get out as a product, we hope, fingers crossed, actual electric energy. So you want to think about it as a conversion between chemical and electrical energy. But to get the electrical energy out, we don't have to put energy in if we're using a volcanic cell. Now, here's some numbers for you to put it in perspective. The average U.S. household currently consumes 1,000 kilowatts of electricity per month. That's kind of mind-boggling. Almost all of this electricity is generated at a remote power plant from either the combustion of fossil fuels or nuclear fission. Thing is, we're kind of running out of those petroleum-based products, and that's going to be an issue. Also, there's a lot of side reactions to that chemistry. While it brings us a lot of energy, it also outputs a lot of things that we kind of don't like, or that we really need to keep an eye on. And even though nuclear energy is incredibly efficient, people really do not like living near a nuclear power plant. We've got to come up with better alternatives, which is why electricity from chemistry, electrochemistry, and anything involving fuel cells is like the hottest research area right now. So here's a couple images of what we're thinking about. So not just for cars, but fuel cells to actually power entire buildings. This is a big area of research. Now, how does this all tie together? Well, again, electrochemical cell, aka a battery, is an oxidation and reduction half reaction that have just been kept separate in two half cells. So every battery that you have is actually made up of lots of little cells inside of it, but then it's wrapped in one big housing because it's just easier to transport, it's safer, keeps all the chemicals inside. We get our electron flow through a wire along with an ion flow through a solution so that we make an electric circuit. This requires some type of conductive solid electrode to allow the transfer of electrons between these two separated half cells. Now, this is typically done through some type of an external circuit. Typically, it's metal, or the hot new thing, of course, is graphite. This requires an ion exchange between the two half cells. So we want to keep them separate until we need to use them, and then we connect them with the wire. But we also need to connect them so that ions can flow between to complete the circuit. This is done typically using an electrolyte solution. Now, here's a nice image of a voltaic cell. We want to remember that a voltaic cell is a very particular type of battery that does not require us to input electrical energy. We get electrical energy out, but this is a spontaneous reaction. This is a chemical reaction that produces electricity. Let's take a look at the circuit in detail. So we've got our two electrodes. Our zinc solid is forming the anode. That's where oxidation is occurring. We've got a cathode, which is solid copper, and that's where reduction is occurring. Then we've got some wires connecting the two electrodes together, and notice that there's also a second point of connection called a salt bridge. That keeps the ions moving, and that actually completes the circuit. The salt bridge is required, again, to complete the circuit and maintain charge balance. If you have a buildup of too much charge on one side versus the other, the entire thing will come to a halt. They really do like to have maintained charge balance, which is why the ions flow in between. So notice that your nitrate is flowing in one direction and your potassium ion is flowing in the other. Now, the thing to do right now is take a look at Chem Activity 48. Pause this video, read Model 1, and complete the questions 1 through 9. Read Model 2 and complete the questions 10 through 12. Don't skip these questions. Take the time right now to pause the video and work on Model 1 and Model 2. Once you've done that, come back to this video. All right, you're back and you've done the questions. So you've gained more information about the types of cells that we're looking at. Here's our old friend again. We've got your anode, which is the solid zinc. That's where oxidation is occurring because zinc solid is going to zinc 2+. It's giving away electrons. You see how the electrons are flowing from the zinc electrode all the way over to copper? Now, it's the copper in the solution. You see that copper nitrate? That copper 2+ is gaining electrons, and then it's going to plate, deposit, precipitate right on the copper electrode. This is also how they actually plate metals on stuff. Now, why is zinc being oxidized and not copper? I mean, is it arbitrary or something? It is absolutely not arbitrary. Here's where we talk about an important concept called cell potential. The difference in potential energy between the anode and the cathode in a volcanic cell is called cell potential. Cell potential depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. Basically, how much does a thing, an atom, want to give up its electrons, and how hard is it to actually rip them off, right? And then on the other side, some other atom has got to be super greedy. That's the situation we need to set up. So cell potential under standard conditions is called standard EMF, or E cell, with that little prime, because that little prime symbol means you're at 25 degrees C, 1 atmosphere for gases, and you're at 1 molar concentration. Now, the sum of the cell potentials for a half reaction is going to tell us quite a bit. This is going to be your E cell. Now, let's take a look at this reduction oxidation table. The stuff at the top is really strong oxidizing agents. That's the stuff that's going to rip an electron off of something else. Now, remember, electronegativity increases up the periodic table to the right. So it makes sense that fluorine is also at the top of this table. Stuff at the top of the table is absolutely going to get reduced. Remember, if you're the oxidizing agent, you're the thing being reduced. So the stuff at the top has got a lot of electron pulling power. It wants to rip electrons off. What about the stuff on the bottom? Well, look, all the way down at the bottom. Lithium, potassium, barium. Hey, that's all those metals that are on the left side of the periodic table. Now, remember, electronegativity-wise, ionization energy-wise, that's the stuff that actually wants to lose an electron or two to be like the next nearest noble gas. They like to be oxidized, right? So the stuff at the bottom of the table is a really good reducing agent, and they like to be oxidized. The stuff at the bottom of the table likes to give away electrons. So let's investigate where our copper and zinc are. Okay, so let's take a look at the very bottom of the table. We're moving up. We've got calcium 2+, sodium, magnesium, manganese. Ooh, there's zinc. We got zinc 2+, aqueous, plus 2 electrons going to zinc solid. It's got a negative E value, reduction potential. Well, it has a negative reduction potential of 0.76 because it really doesn't want to take electrons. It wants to give electrons away. That's why this value is negative. It doesn't want to be reduced. It actually wants to go in the reverse and be oxidized. Now, let's take a look. Keep going up. We got to find copper. Dun, dun, dun. We got chromium, iron, cadmium, nickel, lead, iron. Hey, we're starting to get positive. All right, copper 2. Copper 2+. Oh, but it's to copper 1+. Nope. Oh, there it is. Copper 2+ aqueous plus 2 electrons goes to copper solid. Look at that positive cell potential of 0.34. So copper 2+ is the one that wants to be reduced. Okay, it's positive cell potential, much higher up the table. Remember, we go way back down and we see where zinc is, that negative value. So what wants to happen is that copper 2+ will be the one that's reduced. It's going to rip electrons off of the zinc. And what's going to happen is the reverse reaction of the reduction of zinc. We're going to get the oxidation of zinc. So that cell potential is actually going to be positive, but it's going to be an oxidation potential. Let's take a look at this in more detail. So we got that, and right away we know that the copper is going to be reduced. It's a good oxidizing agent. Copper solid is going to oxidize, copper 2 plus, is going to oxidize the zinc solid, and we are going to get that particular battery because of where their cell potentials are relative to each other. So our copper 2 plus is the stronger oxidizing agent, so it will oxidize zinc solid. Now, we can't measure the absolute tendency of one half reaction. We can only measure it relative to another. Why? Well, because if you have oxidation, you have to have reduction. So we got to put them together to actually get any kind of measurement here. So we do that by actually picking what's called the SHE, the standard hydrogen electrode. That one's set to 0, and then we measure everything else according to the SHE. So the SHE reduction potential is defined exactly as 0. The standard reduction potentials compare for the tendency of that atom, whatever it is, or that ion, under standard conditions relative to the SHE. And then we get that nice ranking in the table that we looked at just a moment ago. Now the half reactions with the stronger tendency to reduce the SHE towards reduction to the SHE have a positive E-red. So that's all the stuff at the top of the table that really wanted to be reduced and is a really good oxidizing agent, had those positive E cell values or E-red values. That's this stuff. The half reactions that actually want to be oxidized, like zinc, and the stuff at the bottom of the table have a negative E prime red relative to the SHE. So for oxidation half reaction, we can write that this is true because oxidation would be kind of the reverse of reduction by charge. So oxidation is equal to the negative of E prime reduction. So if we take a look back at our table here, we can see how that plays out with our zinc and our copper. Copper is going to run in the direction as written. Copper 2 plus aqueous plus 2 electrons is going to go to copper solid. But the zinc is going to actually run in the reverse. It's going to be an oxidation reaction. Zinc is going to be oxidized to form zinc 2 plus and kick out 2 electrons. So that negative 0.76, we're going to run it as an oxidation, and it's going to become positive 0.76. So the half reaction with a strong tendency to occur is the one with the largest positive half cell potential. It's the one at the top of the table, big positive E-red, and it's the one again at the top of the table because they're always ranked positive to negative. When two half cells are connected, the electrons will flow so that the half reaction with the largest positive half cell potential, the stronger tendency, so that one is the one that actually happens. Higher on the table of the center reduction potential means the stronger the tendency for that reactant to be reduced. So remember, top of the table, that's the stuff that wants to be reduced. That's the stuff that's a really good oxidizing agent. If you're low on the table, you want to be oxidized. You want to give away electrons. You're trying to give them away like a Halloween candy that you don't even like, right? Just giving it away to everybody. Okay. So let's take a look back at our reactions from our chemical cell. We've got our two half reactions. Remember, we've got these two reduction reactions. We've got our zinc 2 plus if it's reduced, but you see how it's got that negative E reduction potential, that E prime? But copper, its reduction has a large positive. Now, you might be thinking to yourself, 0.34 isn't that large. Remember, it's all relative. it is large and positive relative to how negative the other one is. So under standard conditions, copper 2 plus is going to be reduced to copper solid. That reaction will occur as written. However, the zinc has a stronger tendency to be oxidized. So zinc will donate its electrons to copper 2 plus. And we're going to get an electron flow that looks like this. These are the reactions that are actually going to happen. Now, let's take a look at, again, Chem Activity 48. You're going to want to pause this video, read Model 3, and complete the questions 13 through 17. Don't skip these questions. Pause the video here and do Model 3, CTQ 13 through 17. Now let's take a look at electrodes. In review, an anode is the electrode where oxidation occurs. Anions are attracted to the anode. It's connected to the positive end of a battery in an electrolytic cell. And the anode is the one that loses weight because it's the one that's being oxidized. Think back to our zinc. Zinc solid was oxidized to zinc 2 plus, which is soluble and goes into the solution, which means that the zinc solid electrode is actually losing mass. Take a look at the cathode. This is where reduction occurs. Cations are attracted to it. It's connected to the negative end of the battery in an electrolytic cell, and this is the one that gains weight. Think back to our copper electrode. It was the copper 2 plus in solution that was gobbling up the electrons from the zinc electrode, and then it would form copper solid, which would plate or precipitate right on the copper electrode, which meant the copper electrode was gaining mass. Remember, this is how we actually electroplate things. Typically, an anode is made of a metal that is oxidized, for example, zinc. The cathode is made of some metal that is also produced in the reduction, like our copper in its copper nitrate solution. But, and you had to have known that was coming, if the redox reaction involves the redox of an iron to a very different oxidation state, or if the redox involves a gas, we may actually use an inert electrode. An inert electrode is one that does not actually participate in the chemistry, but it just provides a surface for the transfer of electrons. You want to think of it as being like a co-working space or like a venue you can rent. The venue doesn't care about your party or your wedding or whatever job you are. It's just providing a space for you to do your thing. That's the same thing that an inert electrode is doing. So here's an example of an inert electrode. Platinum is by far the most popular inert electrode. In this case, we've got our manganese oxidation state, and it's going to go from a +7 to a +2. That's a big change. But all of this chemistry actually happens in solution. So we don't have any solid manganese to plate on or anything like that. But it still needs some type of a surface for electrons to transfer. So that's why we use the platinum one. It's extremely non-reactive, but it conducts electricity. And that's key because the electricity is just our moving electrons. Now, here's where we do some more work. Pause the video, read Model 4 of CA48, and complete CTQs 18 through 21. Also, for homework, do exercises 1, 2, and 4. These are really good summary questions, and they would make great quiz or exam questions. Don't skip these. Now that's the end of this lecture, but we've got a part 2. Make sure you do your homework and review the previous activity 46. Then move on to our next recorded lecture in our electrochemistry section.